Okay, all right. Welcome everybody. I am just trying to make sure that everything is going according to plan. Hopefully the streaming over to YouTube is also working. I'm not really sure. I've got to kind of double some crazy witchcraft going on to make sure that this stream also gets copied over to YouTube. So this is my mad setup over there. You can see the drawer full of crap, in particular the laptop, which is plugged into the modem, which is currently viewing this and streaming it over to YouTube. Just so you know, that modem is a Cisco 887. You should all get Cisco 887s. The router's greatest router made by man. Yeah, I'm so proud of that modem. It's a yeah. Actually, I prefer the 877 simply because it didn't have a fan. The fan annoys me. Yeah. Yeah, I should put a disclaimer video up there. It would be nice to be sponsored by Cisco just because I love the modem. The modem is like 15 years old. They don't even make they don't even make these things anymore. I just think they're great. They're great modems. But we partying tonight, you bet. I was thinking I might read some stories, just painting, and just chill and listen to some music. That's my plan. Roll dial time. You think so? I was thinking something else, but yeah, we could do some roll dial. What time is the party, Jeremiah? It's whenever my children go to bed. Mr. Chicken, I like the Mr. Chicken ones. Goes to Paris. Yeah. I know exactly what you're talking about. Mr. Chicken's pretty cool. So we've still got 5 minutes to chill. Yeah, I don't mind some Mr. Chicken. What else we got? Horrible Harriet. Where can I rock up to the party? Is there a link? Abiram put it up before, but I can just type it in here. There. I'm just going to switch over to YouTube to make sure that that's all working well. I'm not signed in. I think they can hear me. Hey, YouTube friends. Okay, I have to sign into chat. I'm going to do that. I should also mention before you all go off, you need to sign up if you want to put chat things in, I think. I should mention for those of you entertaining the idea of getting a Cisco 887, you need a PhD in computer science to make it work. This is not for the faint-hearted. Yeah, do not. If you've done advanced operating systems, that will probably be okay. Yeah, don't go out and buy one unless you're ready for that kind of thing. Just making sure people can hear. Yeah, sorry. Yeah, I don't mean level 3 computer science advanced operating systems. No. I mean level 9. The stuff. I think do they still give you a T-shirt for doing that course? I'm not sure. If you pass back when I did it, would have been over 15 years ago now. No, I did in 2007, so that's 13 years ago. They gave you a T-shirt if you managed to complete But if you manage to complete the course, oh yeah, you know it, man. I got the modem. Whenever I call up the phone, the internet company and need tech support, they say, "Sir, what is your modem?" And normally you tell them their modem, and they ask you if you turn it off and if you turn it on again, and make sure it's plugged in and that kind of stuff. And I say, yeah, my modem's a Cisco 887. And they say, "Sir, should we send a technician to your premises?" Yeah, that's the Anyway, sorry. Yeah, that's my flex. Joanne, is there a class on Monday? Monday is a public holiday, so we're going to Jaya and I are going to pre-record some lectures and upload them sometime over the weekend, presumably. We're still using the first notes booklet, right? That's right. We're going to be doing well. We're only up to page 4. Probably move a little bit faster, but not too much faster. Let's make this a bit bigger for me so I can. There we go. Maybe I can zoom in. Oh yeah. It looks like my internet connection is poor. Excuse me. Sorry, I just got a little pop up. We can hear you. All right, cool. People on YouTube can hear me. Awesome. Okay. Pre-recorded lectures are on Moodle, not Blackboard. Yeah, I think I just have to make a recording and I'll just upload the MP4 to you. What app am I using to edit the file? It's called, what is it called? I'll type it in here. It's called External. It's a PDF annotation thing. It's what came with Linux. Personally, I'm a BSD kind of person. But I got this computer and it's too modern to run NetBSD, so all free BSD. So I had to run Linux, and that's my second choice. The YouTube thumbnail that got sent in to me as part of the challenge. I think I can share that. Can I share that? The thumbnail was golden. What distro? I think it's 17 point something. It's just whatever the Ubuntu thing is. I just got whatever Ubuntu it was and installed it. I'm not really into the Linux. But ask me what version of NetBSD I'm running, and man, I just upgraded from 9.0 beta to the proper 9.0. Yeah, that's where my heart is. Do you have your BSD mug on you, Abhi Rahman? I've had so many. How do you know I have had a BSD mug? I've had so many of those mugs, and I just keep destroying them. Like I just walk around everywhere with them, and eventually I crash into something, and the handle falls off, and then I have to go buy another one. And at this point, I've just bought them so many times. It was in one of the. Yeah, loving that mug. No, I've just destroyed them too many times, and now I don't have one. Yeah, the School of Maths also has these free mugs, and so I've got so many, mugs. Get my UNSW sponsored mug. I get my mugs for free now. I don't need to buy the NetBSD mug. UNSW, I wouldn't say they give them to me, but they're in the storage room, and the storage room ain't locked. So I just get my mugs from the storage room. I'll go get a UNSW mug. Hold on a second. We'll start the lecture in a minute while I go get a cup of tea. UNSW, this stream is sponsored by UNSW. If you want your UNSW mug, that costs about $4,000 from the School of Mathematics and Statistics. I get it. I get my cut of about 1%. right. All right. So, UNSW School of Mathematics and Statistic mug. There you go. I wanted to get one of those, you get those university jumpers that say, what university you go to. I wanted to go get one of those University of Sydney jumpers and just wear it around UNSW, just to, in case, just for the lols. All right, coffee or tea? Right now it's water. I don't have time to make coffee or tea. We're supposed to be doing math. Yeah. except when I meet like the vice chancellor in the walking down the main walkway, then it'd be all over for me. Never buy the uni t-shirt. Yeah. All right. Posting my UC merch. Cool. All right. I think we're getting ready to actually start this stream now. So I've said all the controversial stuff, and now I'll start recording. Here we go. So things are being recorded. I'll say more and more controversial things once I stop recording. Let's go. Where were we? There we go. Okay, so you might remember last time we just saw a bunch of axioms. This was largely an effort to take mathematics, this wild world of mathematics, and create rules so that we could understand what was mathematics and create mathematics just by purely mechanical calculations. This was about 100 years ago. People who made mathematical calculations were called computers. They were actual people who just made routine calculations. And they did things based on the rules and nothing else. You had to follow the rules. That was how it was. So you could use the rules. We've only got 10 rules, so it's not so bad. We could use the rules to prove this thing that, where's my pen? I'm sorry, there we go. To prove that, why is my pen not working? Yeah. So if I can do this, that works, but why is my pen not working? Come on, pen. Nope, my pen is not working. I'm just going to unplug the tablet and plug it back in again. 1, 2, 3. Yeah. Come on. Nope. Okay, let me close that and open it up again. Close. Sorry, just wait. Bear with me for a second. Discard that. Open it up again. Open. Can I write on this? Hey, I can write on it now. Okay. That one. Allow. Okay. So there we go. Okay, good. La-di-da-di-da. Okay. Zoom in. So let's prove that 0 times u is equal to 0. And you have to, now the trick here is you have to prove it using the rules. And only the rules. So we'll start off with u. U is equal to, well, that's going to be, sorry, not u, 0. Let's start off with 0. The 0 vector is equal to, well, it's equal to u minus u. And which axiom says that so? That is axiom number 5. The negative, the existence of negative. Maybe I'll add, the axiom 5, the one about negatives. So there is a u that exists. And this is equal to 1 times u minus 1 times u. And this is by axiom 8, which you might recall is the one that we didn't bother to give a name. So let's call it the unnamed. the unnamed axiom. And then we can use the axiom, which one is it? It's number 9, axiom number 9, to say that, well, we can write this as 1 minus 1 times by u, which is by axiom 9, and this is equal to 0. The scalar 0 because 1 times 1 is equal to u by because 1 minus 1 equals 0 is and that's arithmetic from the real numbers. The axiom has no name. Yeah, it's just got no name in the notes, so we're calling it the unnamed axiom. This one here is one of the distributive laws. So we can talk about axiom 9. Let's call it the distributive. Now this is so how do we refer to them? By their numbers. You would refer to them by their numbers. The names are really just for my benefit. Now this is very mechanical, and it was described to this fellow. Let's where are we here? Daniel teaching 1231. This guy. It was described by this guy as a very mechanical procedure, and he's like, and let's get this in the right proportions. There we go. He's like, very mechanical procedure. You mean like something that could be done with a machine? With a machine is and they're like, yeah, with a machine. He goes. He's like, you mean mechanical like a machine? And then he goes and builds a machine that actually does this stuff and calls it a computer, which is where we have no, this is Alan Turing, and goes and builds a machine, changes the entire world, wins the Second World War, and gives us all lovely telephones and computers like we have right now. Unfortunately, so the question was, do we need to memorize the axioms in the test? No, son. You build a machine that does it all for you. If you're like Turing caliber, you can build a machine that does it for you, or yes, you can memorize the 10 axioms. Your call, which one you want to do. Yeah. Look, there's a few axioms you probably want to. Yeah. Let's leave it at that. Is one of my it's actually really sad that Alan Turing killed himself because he was persecuted for being homosexual. It's very particularly sad. I find it particularly sad because I could have actually met Alan Turing. He conceivably would have still been alive at the time that I was around. So guy wins the war, saves millions of lives, invents computers. Society still hates him. So, yeah. So that's my little rant. Anyway, let's move on. Main example is given in the printed notes. So, what we're going to do. So yes, there are 10 axioms. You can prove things with them in a very mechanical fashion. Like you literally go from one step to the other. Mechanically as a machine would. Subspaces. Okay, so this is where we're really this is the core of the subject right here. Consider a plane passing through 3 points. Plane passing through 3 points. Now, one of these points significantly is the origin. Go back to my little pencil thing. There we go. One of the points is the origin. That's kind of important. This plane. The plane contains the origin. If you're thinking of axiom number 5, is it axiom number 5, the one about the existence of 0? Let me just go back real quick and check. Yeah, it's axiom number 4. Axiom number 4, thank you. Axiom number 4. If you're thinking of axiom number 4, you're doing it right. Contains the origin. Consider a plane which contains the origin and passes through some other points as well. From MATH1231, we know that the equation of this plane is this thing. Yeah. Are you wearing pajama pants with that suit, Daniel? No. I'm wearing. I go all out. I go all out for you guys. That's how seriously I take this. given any two vectors, on this plane, then there's now this is the, I'm going to stop looking at chat for a moment. It's getting out of control. Given to any two vectors on this plane, their sum also lies in the plane. So let's just have a look at this. So here's my two vectors. Here's the origin, and here's one vector. Let's call it v1. And here's another vector. Let's call it v2. Oh, we do it in red. v2. So this one's v2. This one's v1. And the origin is right there. Damn it, I should have done v1 in black. v1 equals. Good. So the plane, if you will, looks like a two-dimensional piece of paper sitting on top of this thing. So if you like, you can imagine just a little line extending through v1, and then parallel lines like that, and then through v2. Similarly, you've got parallel lines that are going like that, da 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 da, and this kind of crisscross thing gives you a two-dimensional chessboard, if you like, or thatch, or whatever. Gives you a two-dimensional space. Gives you a two-dimensional space, and that two-dimensional space, everything on it is the span of those two vectors. There's some important things about these spans. If you take two vectors, v1 and v2, then the sum v1 plus v2 is on there. So here's v1 plus v2 being the sum of those two vectors. Or in fact, you can go any amount of this along this black line and then any amount down the red dashed line and still be on the plane. In essence, what this says is that you take any two vectors from the span, you add them, it's in the span. So does any elongation, i.e. scalar multiple of a vector. So if you take v1 and you take lambda times v1, guess what? You're still on that piece of paper. And it contains zero. And it contains zero. That's kind of important. There's zero right there. Boom. Zero. And you get all the other, hang on, Richard says, just for clarification, a vector space is a set of vectors that complies with all the axioms, right? Not compiles, complies. Yes, that's what it means. Now, we just looked at three of them. We looked at the existence of zero, we looked at the addition, we looked at the scalar multiplication, and you get all the rest for free, because you take advantage of the fact that these vectors that you've got, these ones in a plane, live inside a known vector space. So the plane actually inherits all the axioms, all but three of them, from Big Daddy vector space that it lives inside. So you only ever have to look at three of them. You only need to take a span and let me insert a picture here. Picture, that one. Whee. I thought this would be better. I just cooked this up with GeoGebra. So you can see, cancel. You can see the, this is like the two-dimensional plane. There's the two drawn to scale, v1 and v2, as we talked about before. There's our two vectors going between the points. And if you take any amount of this vector, you can add these two things and you still get on the plane, or you can stretch it and you get on the plane and that origin's on the plane, and everything else, that whole distributive law, existence of distributive law and all that jazz, just comes from the fact that we're doing this in R3. So, all right, Daniel, what do you mean when you said subspace? I'm a bit confused by that term. Okay, so here's I'm going to use that to segue right into here. If V, what I mean is if V is a vector space and S is any subset of V, which happens to also be a vector space, then we say S is a subspace of V. It's a vector space living in another vector space. Think about you've got three-dimensional space, which we're living in right now. You know all about three-dimensional space. And then you take a two-dimensional piece of paper, which lives on that space. With a two-dimensional piece of paper. Now, the two-dimensional piece of paper, just infinite two-dimensional piece of paper, I should say, looks just like R2, but it's living inside R3. Bold of you to never assume, Georgia, sorry about that. Big apologies to all you 1, 2, 4 and higher dimensional beings out there. Yeah, I don't mean to prejudice and assume which space you're living in. Damn it. Okay, getting back to the thing. So you know what two-dimensional space looks like? R2, probably being the most familiar vector space that to us, because you've used R2 a lot in school to draw two-dimensional things. Okay. Now, you can think about R2. You can think about it two ways. You can think about that piece of paper that you're drawing your things on as being the entire universe, and nothing exists outside of R2. Totally legitimate way to go about drawing things in 2 dimensions. Or you can think about there being a third dimension which sticks out of your piece of paper, and that your 2-dimensional piece of paper is embedded in this larger 3-dimensional space. Makes no difference to the way you do your drawings, but it's a vector space, a 2-dimensional vector space living inside a 3-dimensional vector space. And that's the idea of a subspace. You've got a 2-dimensional space, a 2-dimensional thing living in a 3-dimensional thing, or a 3-dimensional thing living in a 4-dimensional thing. So a subset is always 1 dimension less. Subspace, no, you can have something can be a subspace of itself. Rn is technically a R2 is a subspace of R2. Doesn't have to be a lower dimension. Can anyone think of a 0-dimensional space? Can we have a 0-dimensional space in chat? A point, not just any point. No. Empty set, excuse me. Empty sets have to have at least the 0 vector. I saw it there. Now chat's going crazy. I can't see it anymore. Sorry. I'd see at least Aline and Joel Paul both saying 0. Ethan Young, 0, 0. Ethan Young, interesting answer. I just want to comment on that for a second. So most people saying 0. Yeah. Ethan said 0, 0. Now we can think about this. So his 0 is embedded in R2. And a lot of other people just said 0. So in R. So in this case over here, we have a 0-dimensional space in a living So that one's a 2-dimensional space, a 0-dimensional space living inside a 2-dimensional space, and this one's a 0-dimensional living in 1D space. See, R just being a 1-dimensional thing. All right. All of you who said empty set, you broke the law, because axiom number 4 says you have to at least have the 0 vector. So sorry for everyone who said the police are coming for you now. If you said empty set, they know where you live. We have your IP address. I'll see you again next term. Try again next time. All right. Okay, so we've got vector spaces living inside other vector spaces. The good news is vector spaces pretty much are either going to be a single point, the origin, a set containing the origin. That's a 0-dimensional space. 1-dimensional spaces look like lines. 2-dimensional spaces look like planes. 3-dimensional spaces look like R3, and I have no way to imagine what 4-dimensional spaces look like, but they all kind of characterized by their dimension. So when you talk about a plane, to me, it's always a sheet of paper. It's always that 2-dimensional space. And it can be living inside a two-dimensional space or three-dimensional space or some kind of space of not less dimension. Can vector spaces be bounded, Richard? Ooh, I don't want to go down that rabbit hole, but yes. Yes, but not in this course. Let's put it that way. Yeah, let's not go there. I'll get way too distracted. Okay, let's get back to the notes. A set S inherits most of its vector space axioms simply by belonging to a known larger vector space. Typically, this one is going to be something like R2, R3, a known. So you get a lot of the things simply by being in a known vector space. The only things you need to check, so you get given a set and say, here's Christmas, and I give you a set. And you want to know if what I've given you is a vector space. You only need to check 3 things, because the set of elements comes from R3. You know R3 is a vector space, so you know it's automatically going to satisfy the distributive laws and a whole bunch of other things. The only things you need to check are that it contains the 0 vector, because vector spaces have to have the 0 vector. You also need to check that if you add 2 elements from S, they have to be from S. So you start off with 2 elements in the set that I gave you for Christmas, and add them together, then the output is still in S. That you don't somehow escape the set. And by that, that's what I mean by the cross. I know there's a question in there about crosses. This notation just means addition takes 2 elements and outputs 1. And similarly for scalar multiplication, if you take anything in the set that I gave you for Christmas and stretch it, then it's still in the set that I gave you for Christmas. That's what this means. So that's what this means. The axioms for 0, addition, and scalar multiplication are still satisfied. Everything else you get for free, and that is the subspace theorem. Take a set which is in a known vector space, and that's going to be the case for us always in this course. You take a set of a known vector space, it's going to be a subspace, and that means space in its own right if it satisfies axioms 4, 1, and 6. That is, it contains 0, it's closed under addition, and closed under scalar multiplication. You do not, to prove this result, you only need to check. Yeah, we're not going to prove this result. Let's just get into some examples. Note showing that a given set S contains a 0 vector also checks the set is non-empty. Let's not talk about that anymore. The easiest is often the first thing you do is check that it has 0, simply because that's the easiest one to do. Does a subspace have to be a vector space? Yes, Damien, a subspace is a vector space. Notably, it's a vector space living inside another vector space. So, yeah, that's what subspace means. So here's a set. It's the set of all x in R3, a known vector space, mind you, and it's given by this Cartesian equation. It happens to be a plane through the origin. Is it a subspace? Lewis says, so the subspace theorem also proves SMT is a vector space. I'm not sure what SMT is. Something is a vector space. Yes. So something is set in this particular case. It proves a set is a vector space. That's probably the easiest way to imagine it. So here we just have a set. When someone asks you, is it a subspace, you only ever answer with the subspace theorem. You do 3 things. 1, check. So here we go. Check 0 is in S. Since I don't think I really want to put numbers here. Let's just get rid of that. Check 0 is in S. Since 0 is equal to 0, 0, 0 is an element of R3, and 5 times the first component minus the second component plus the third component is equal to 0, then 0 is in S. Sometimes I see people write, obviously 0 is in S. I hate that word, obviously. Never use the word obviously in in mathematics. If it's obvious, prove it. Show me how obvious it is. Obviously 2 plus 2 equals 4, shady. I'll accept that. But it's generally speaking a bad idea. When they ask you to show something, you don't say obvious. No. You show it. And here you're required to show that 0 is in S. Well, give me something. Don't tell me how obvious it is to you. Just show it to me. The other thing we want to check is check it's closed under addition. Now, what does that mean? What does that mean? You start off with 2 elements in S. So that's addition. If say A and B are in S, then, okay, you have to start off with A and B are in S. What do you know about A and B? Then A equals A1, A2, A3 is an element of R3, and 5A1 plus, so that's a minus, A2 plus A3 equals 0. And what else do I know? Well, I know B. B is not a matrix or something crazy. It's a vector from R3. It looks like B1, B2, B3, but more than a vector from R3. It satisfies this equation. Okay, now I need to show that the sum is in S. Now, A plus B is A1 plus B1, A2 plus B3, A3 plus B3. I need to show this is in S. It's in R3, and this makes me really pleased in my heart because the definition of S says take things in R3, and here, boom, I showed it was in R3. It's not an amazing discovery. It is, but it is literally what it means to be in S. So you wanted me to show it's in S? Here you go. Here it is. It's an element of R3. That's halfway to being in S as far as I'm concerned. And this thing satisfies the equation for being in S, or the condition, if you like. 5A1 plus B1 minus A2 plus B2 plus A3 plus B3. This is supposed to be equal to 0, remember. This is supposed to be equal to 0. Is that supposed to be a 2? Yes, it is. Thank you for letting me know. 2. And this thing, well, that's equal to, now I'm just going to collect all the terms with an A in it. 5A1 minus A2 plus A3. I'll put some brackets around that. Plus 5B1 minus B2 plus B3, which is equal to 0 plus 0 by assumption. That A and B in S equals 0. Hence, A plus B is in S. Now, there's 2 things I want to say about this. The first thing is that whenever I see someone start a proof like this and end it like this, it just makes me pleased. Sometimes I feel like I don't even need to read anymore. This person knows exactly what they're doing. They know that they need to start off with elements of S. They know they need to conclude that the sum of those 2 things is in S. Now, critically, you need to use the fact that A and B were in S to get from here to here. If you start from here and end up here and you haven't fundamentally used the fact that A and B belong to S, you are doing it wrong. You need to use the assumption that A and B were in S somewhere along the line. Now, I appreciate this might be new to you. I did B3 twice, did I? Oh, so that might be an older comment. Do I need to prove zeros in S first? Yes, I do. That's this one here. I do need to prove zeros in S, and Zach, I've already done that. Lachlan's obviously A plus B are in S. Lachlan, once you have a PhD in mathematics and make it to the rank of professor, you may say, obviously, A plus B is in S, and I'll have to just nod and listen to you. But at this stage, you're being in your mathematical career, you're being asked to prove it. And if you say obviously, then that's not going to work out well for you. It may be, I hope it's obvious to you, but you still need to prove it. The question is not to, sorry, I'll just leave you alone now. Sorry. Okay, I've got one more thing to do about this question. I need to check that it's, prove S is closed. S is closed under scalar multiplication. That one. So if lambda is any real number and some vector A is in S. Okay. Now I have to start off, it can't be some vector, any old vector, it has to be from S. I need that piece of information. Then A is A1, A2, A3 is an element of R3, and 5A1 minus A2 plus A3 equals 0. So to check for closure under addition, we just assume A and B are in S. Absolutely. You need to assume A and B are in S and then conclude that A plus B is equal to S. Is in S. So lambda A is equal to lambda A1, lambda A2, lambda A3 is in R3, and 5 lambda A1 minus lambda A2 plus lambda A3 is equal to lambda times that stuff. Just take that common factor out. Equals lambda 0 times lambda by assumption. So here, I'm just being really clear about when I'm using that assumption. I need to use that somewhere along the line. Equals 0. So lambda A, damn it. So lambda A is in S. So I start off with two elements, any scalar and any A, and I show that scalar times A is still an element of S. Damien says, I'm confused what we are proving to check these three things. Are we proving that the subspace is a vector space? You're proving the set S. Up until this point, we didn't know if S was actually a vector space. Turns out that it is because it contains 0. It's closed under addition. It's closed under scalar multiplication. And all the other 7 axioms, it inherits from Big Daddy R3 that it lives inside. So this is actually a vector space living inside the R3. But it's a vector space in its own right. It happens to be a two-dimensional plane, just so you can have some kind of geometric understanding of what it is. It's a two-dimensional thing, so it looks like R2. It looks just like R2, but it happens to be embedded in three-dimensional space. So when you talk about the things on this plane, obviously it inherits. For the second question, why are we proving scalar multiplication? I'm sorry. No, I'm still doing part. This is part 1. This is from part 1. I had to finish it. Yeah. Okay. Yeah. Okay. Now I've confused half the class. Okay. Let's do question 2 now. Question 2 is real easy. This is exactly the same space, except it's moved up. It's moved to a different place. So it's like a parallel piece of paper, but critically, it doesn't go through the origin. Doesn't go through the origin. So it looks geometrically, it looks like R2, but it does not contain 0, which means not a plane. And that's the easiest way to get around it. To show that it's not a plane. Since let 0 be equal to 0, 0, 0 is an element of R3. 0 is not in S, since 5 times 0 minus 0 plus 0 is equal to 0, which is not equal to what it should have been to be in this set 3. Daniel, you need to see the comment from Samuel. Long ago, the 10 axioms lived in harmony. Then everything changed when closure under scalar multiplication attacked. Only 0, the superior axiom, could stop it. But when the dimensions needed it most, 0 ceased to exist. Awesome. Thank you for that. Samuel, HD for you. Let's go over here. Question 3. How interesting. Now, it's the good news is when you're just walking through the street, you're having a good day, and someone throws a set at you and inquires of you, is it a vector space? And it's just some crazy stuff you've never seen before. The good news is you only ever use the subspace theorem to prove this. You know automatically it satisfies the 7 axioms from Big Daddy vector space R3. You don't even need to look at those. It gets them for free. It was born with them. The only things you need to check are, does it contain 0? Does it remain closed under addition? And does it remain closed under scalar multiplication? Let's just have a think about this one. Does it contain 0? Well, actually it does. Because if you let x be 0 is the 3-dimensional vector 0, 0, 0, and I might just say 0 is in S, since 0 is in R3, and 0 times 0 plus 0 is equal to 0. So actually this one, let's just draw a line there. So it does actually contain 0. What about closure under scalar multiplication? Now, we're gonna shift gears a little bit here. Normally, when you're proving something is a vector space, you need to prove it in all generalities. You need to take any A and any B from the space and add them up and show that their sum is in the space. Any possible things whatsoever. You take general elements in order to show that every possible, as a kind of way of doing a lot of things together. So you don't need to take every single plate. Essentially, what you're doing is taking all the possible values of A and all the possible values of B and showing the sum is in the set. But when you're proving something breaks the law, when you're proving it breaks the scalar addition law, you only need one element to show. You only need to show one time it breaks the law. One time. So don't mess around with all these generic arguments about let A be any element of the set. No. Show me exactly what vector you're taking out of here and exactly how it breaks it. So here we're going to be really clear, really clear. Let lambda not be any real number. Let lambda be 2. And A is going to be an element of my set, and that's going to be, let me see now. Let me see. I want, what do I want? 1, 1 minus 1. Now I had to think there for a moment. Now I need to prove why, Steve, why choose, okay. Let's let lambda equal something else and see how that works out for me. Why do I let lambda equal 2? Because I've done this before. But let's see what happens if I choose lambda equal to 1. I'm going to change it back to 2 later. No, actually, no. I'm going to leave it as 2 for now, and then maybe you can tell me why 2 is a good idea. Yeah, I'm going to leave it as 1. Sorry, I'm going to leave it as 2, and maybe you can tell me why 2 is better than 1 here. And A is in that. Then A is in S because 1 times 1 minus 1 is equal to 0. Okay. So not because 2 is just better than 1. That's why I chose 2. So what have I done here? I've taken any scalar and I've taken an A from S, and I showed it was in S. I showed it was in S. Okay. If S then 2A is in S. Now, then 2A is in S. Now this is where the wheels fall off. But 2A is equal to 2 minus 2 is an element of R3, and so it's in R3, it's got the right type, and 2 times 2 minus 2 is equal to 2 is not 0. Not 0, hence 2A is not an element of S. And the assumption can't spell multiplication. And our assumption was false. Okay. So now, okay, Alec has got it. That's why. So imagine in these scenarios where you're showing a set is not a vector space, you are really the prosecution, and you need to produce evidence. You need to find that evidence. It's a little bit of investigation has to go on. You have to find the evidence that shows S is not a vector space. Now, sometimes S will behave as a vector space. Sometimes it will actually contain 0. Sometimes, and in particular, often when lambda is equal to 1, lambda times A will still be in the set. It's your job as the prosecution to find the values of lambda and the values of A where S breaks the laws. That's why it's really important to be clear about exactly what values you're talking about. You need to find those values for which the set breaks the laws. How do you know to prove it's a vector space? Actually, addition would have worked as well. Steve, it is. Steve says so. Trial and error. Steve, I'd say it usually takes about 2 guesses. So you have an initial guess, and you try it, and if it ends up not doing what you expected, then don't throw away all that effort. Find out where it went wrong, and then fix it. For example, if you chose lambda to be equal to 1, you might notice that oh geez, that wasn't right because it didn't quite get me the answer I was expecting. So maybe I'll go back and change the value of lambda and then see what happens. So don't throw it all away. Don't just keep making random guesses until the cows come home. Just you take your initial attempt, and if it doesn't quite work out, tweak it a little bit to make sure that to get the result you're desiring. How do you know which axioms it doesn't satisfy? You don't know that beforehand. You don't know beforehand if that's the case. You have to test it. It's an investigation. You can't use 111 because it's not in S. Sharon, exactly. Sorry, Shannon, exactly. It's you have to check the thing you made. You can't just take any vector here. You have to take a vector from S. It has to be from S, and you need to check it's in S as well. If you start showing me, oh, lambda's 2 and A is some vector I've never heard of, doesn't even belong to S, as the judge, I'm not convinced by your prosecution. You're supposed to show that it doesn't obey the scalar multiplication law. And the law says you take an element from S. And if you fail to show me that the element is from S, then I don't even need to look at your witness. It's not in S. The law says nothing about what happens to elements not in S. Get out of here, prosecution. Case dismissed. Yes, you can take that. Yeah, okay. Let's probably do one more of these. Yeah, let's do one more of these. This is a nice example. So this is a good one for us to finish on. And then I'll do the competition. And I've got lots of space. So show that the set of all solutions to this thing, AX equals 0, forms a subspace. Oh, hang on. There was a question. I can't see. Okay, how could you tell from first glance? You have to prove that S wasn't a vector space? Number 3, as opposed to being one. So in number 3, how did I know it wasn't a vector space? So I switched my thinking into the world of geometry. Vector spaces are the origin, lines, planes, 3-dimensional spaces and 4-dimensional spaces and so on. So geometrically, I'm thinking, right, I look at this thing and I ask myself, is it a plane, a line, a point, a 3-dimensional space? And this thing here, this equation that I get given, this x1 times x2 plus x3, is none of these things. It's a curve, probably maybe some kind of I don't know what it looks like. But it doesn't look like a plane, and it doesn't look like a line. These planes and lines have very fixed Cartesian equations. So I know that this is not the Cartesian equation of a plane or a line. So I'm immediately suspecting that this can't be a vector space. It's a weird hyperbola thing, says Leon. Thank you. Yeah, so I recognize from its geometry that it's not something I don't recognize its geometry. That's probably how I would describe it. I don't recognize it as a plane. I don't recognize it as a line. It's some other weird thing that's not going to be a vector space. Okay, awesome. Cool question. Thank you. Show that this. So, question 4. Show that it's not. Show that this forms a subspace of R3. Again, you're having a nice day. You're walking along, having a good time. Someone throws a weird space at you and demands to know if it's a subspace. You have only one option, and that is to use the subspace theorem. Prove. So I'm gonna define this thing. Let Ker A equals. This is also known as, I like this description better, the killing set of A, which is the set of all X in R3 such that X is killed. X is killed by A, basically. That's what it says. Prove 0 is in the kernel of A. It's included in my space known as the kernel. Ker means the killing set or kernel. And it's the set of all things that A sends to 0. Since 0 is in R3 and not add, and A0 is equal to 0, then 0 is in the kernel. Does 0 get killed by A? You bet. You just you feed in the 0 to this matrix here, so you could even compute A times 0, and you would find it's equal to 0, and therefore 0 is sent to 0 by the matrix. Anytime someone throws a subspace at Daniel, he never gets hurt because it's always able to solve the problem in a few seconds. Prove Kerr. These days, I'm the one throwing the problems actually. So closed under addition. If x and y are in the kernel, then AX, what do I know about AX? AX is killed by A. And AY, what do I know about Y? It's killed by A. That's all you know. These are fatalities. All you're told is that X and Y, they're killed by A. What happens to their love child, X plus Y? Then A times X plus Y is equal to AX plus AY. Oh wait, you don't know what a linear transformation is because I haven't told you what a linear transformation is yet. I'll just leave it as that. Equals 0 plus 0 equals 0. Hence, bad news, X plus Y also killed. Prove, final thing. Kerr. If X, I just have to scroll down a bit. If X is in the kernel of A and lambda is in the real numbers, then what do I know? Well, I know that AX equals 0. Then what happens to A times lambda X? Well, that's just equal to lambda times A of X, which is lambda times 0, which is equal to 0. Hence, lambda X, what happened is also in the kernel. So the kernel contains 0. It's closed under addition. It's closed under scalar multiplication by subspace theorem. Kerr. Alrighty. So do we always need to prove this or / prove closed under addition multiplication? To prove it's a subspace, yes, you need to prove all those things. To disprove it, you only need to show it doesn't satisfy one of these axioms at one time. Okay, so that's time to finish up today's lecture, except for the competition. So let's do this. I have to open up a window with some things in it. 231. Alrighty, so let's I have to share a different window. No, not GeoGebra. Damn it, I shared the wrong thing. Sorry, let me share something different. You weren't supposed to see that. There. Whee! Okay, here we go. So this entry, I like this entry. Thank you. Who said this in? Quinn. I'm not sure if I'm pronouncing your name correctly, but I love the one about planes. The competition this week was to enter your answer answer any math question as a comic. Here. So what you're telling me is that if I find the determinant, it will give me a plane. That's what it says in the course pack. And she solves the determinant. Now what? Maybe if we graph it, it will show us a picture. It looks nothing like a plane. Ah, now it does. Awesome pun on the idea of planes. Thank you very much for that one. I can't see chat right now. I'm just gonna have to rush through this. I'm sorry. I like this one. Oliver sent this one in. Does 0, I thought this was very topical. Can you even see what I'm looking at? You can. Okay, awesome. Does 0 exist? If it did, we could understand nothing. Evidently, they're understanding nothing here, and 0 does in fact exist. And of course 0 exists. That's axiom number 4, man. Like, what do you even talk? Why even question it? Does 0 exist? Next one. This is the I couldn't resist this one. Awesome, dramatic chipmunk. Yes, I am the dramatic chipmunk. Now everyone knows it. The friendship paradox. Okay, I like this one. This one explains why you don't have any friends. The phenomenon shows that you're more likely on average to have less friends than your friends. That's kind of confusing. However, it's all up to sampling bias. This is from Julian, by the way. Let's say that Gauss joins your friend group. Since Gauss is popular, he has many other friends. Thus, all of your friends are now friends with Gauss, raising the total average number of friends of your friends, number of friends your friends have compared to you. If we randomly sampled someone, say you, then and then average the number of connections or friends represented by the lines, your friends would have we would find out that you have less friends. Your friends have more friends than you. That's what it says. But it's not because you're unpopular, it's because of sampling bias. So I wanted to talk more about that one, but I need to get through to the other entries. Modern problems require modern solutions. This one's from Brinzy. Hard math, and you can see what's being thought over here, and then hard math gets solved by some weird method, A+. Thank you, Brinzy. This one was too close to home for me. I've seen this happen way too many times. But the winner is from Ada. Thank you, Ada. This one's awesome. I won't go over it now because we've got, but it was so awesome that it got posted on the School of Mathematics and Statistics Facebook page. So you can all go check it out there and give it the attention and love that it deserves. So big shout out to Ada for an awesome entry. This one I loved it. Next week's entry. Yay, Ada. Can we get some hearts in chat for Ada? That was wicked. The competition for next week is to write a piece of mathematics with no words whatsoever. You have to prove something or answer a question or do some mathematics, and it has to be a true thing about mathematics. It has to be clear to me what you're proving. You can say what it is, like that you're proving up the top, but your response, so you can say what the question is with words, but your response has to be only a picture. All right, here we go. So send those to me by Thursday, and I'll write down in the I'll put a post up on Moodle about what the next week's competition is. Cool, we are right on time. Jaya, are you around? I'm ready to hand over. Are the submissions anonymous? They are anonymous if you want them to be anonymous. I will never share something without your permission. If you want to send an anonymous entry, that's totally fine. Jaya is coming. Do you play Minecraft? I can't play video games. I'm sorry. Oh, here we go. Yep. Jaya,
yeah.
Yes,
I'm on.
Yeah, you are on. So you can share your screen. I'll keep the YouTube thing going.
Okay. You may want to yours is on still. Your screen.
Yeah, if you just start sharing your screen, it'll just flip over to your thing.
Okay.
Yeah, and Jaya, people are asking if to keep the chat open so you can see them asking stuff.
Yeah, it's all right.
Awesome.
Let me share the files.
No problems, everybody. My pleasure. I'll see you. There'll be an upload for Monday's lecture because we missed it out due to the public holiday. So Jay and I will both upload a lecture for Monday, and I'll see you on Wednesday or tonight, depending on if, yeah.
I think you, okay, so once you, I can put my file,
Yeah, go for it.
I can share the file once you have taken yours, I think.
Oh, okay. If I click this, I'll click stop sharing. There we go.
Okay, let's see. Let's start again. Something wrong here?
I haven't seen anything yet, but
Yes. Just a second. I think I have to.
hello, Jay, are you there? Oh no, he's coming back. I'm sure he'll be back. Cool. Cool. I had more time than I was expecting to. Daniel, where will the recorded lectures be posted on Monday? Just onto Moodle. So I'll just make an MP4 and post it on Moodle and throw up an announcement so you can see where that ends up. So there's no live lecture on Monday. I'm kind of tempted to do one on Monday anyway. I mean, there's no time between now and then for me. I basically have to. No, Jeremiah, unless I decide to just do the lecture on Monday anyway, as a live thing, and maybe that's it. Maybe that's what I do. Hello. Oh, here we go. Okay, cat. Everybody, here's a cat. This is definitely the internet. We have cats. This is Charlotte. She does what she pleases. This is my daughter's cat. She hello. My daughter had, the deal is when you go to school, you get a pet. And so my daughter had decided that she would call her pet Charlotte, and she decided this well before she went to school. And then when the cat became real, she just kept the name going. Chicken or riot? Chicken has a rival. I don't know who Chicken is. Mark Chi has a cat. Cool. Cool. I have to get together with Mark Chi and do like a double stream with him. That sounds awesome. That would be cool. Yeah, we can have a crossover episode. I'll teach comp and he can do math. Then nice. Double the cat happiness. We'll have a cat party. Oh. We'll find a way to make it happen. Do you want an autobiography on the Wikipedia? No. I can just imagine how that would read. Daniel, famous for having a cat and a Cisco 887. Yeah, I can live without that. Thanks for the offer. I don't know where Jay has gone. Maybe I'll check my email. Am I streaming tonight? Casey, yes, I'm streaming tonight. Just checking my phone to see if I've got any. Oh, here we go. Yep. Jay, I can hear you.
Yes.
Hey, we're cooking. Nice.
Okay. So it's still recording, right, Daniel? So
Still recording. I'll keep the YouTube thing going, so you're all.
All right then. Okay. So might give a few minutes for students to have a break before we start the calculus. Still, this maybe. Okay, I think we'll better start. Chapter 1b is okay.
Jay, can you just press focus? Oh, there we go. Yep, you did it.
Okay, yes, just focusing issue here. All right, so we're going to talk about today tangent planes, normal vectors, then error estimation and chain rules. I'm not sure we can get to chain rules today. Let's see. So the first question, what's the tangent plane? Okay, let me show you a picture here. Oops. Oh, okay. Here comes that. So you have the surface here. You can see the line L1. L1 is that tangent line has the slope dx. df on dx. So if you see that, you see the blue line there? Blue line is the cross section of the surface, and here equals y naught plane. You see that the line, blue line is on L1, it's a tangent to that blue line there. Okay, so you see that the curve there that lies on the plane y equals y naught and the surface. Similarly, if you look at the second line, L2 here, L2 is to the blue line, which lies on the surface, and the x equals x naught plane. Okay? So these two tangent plane, the tangent plane is formed by these two tangent lines. Okay? And then we want to know what the normal vector is. The normal vector is the vector perpendicular to the tangent plane. So, for example, if you look at a surface like this, let's say, so that's your point x naught, y naught, z naught on the surface. Okay, so you have a tangent plane, something like that. So that's your tangent plane. And the normal vector is the vector which is perpendicular to the tangent plane. Okay? Now, so that let me call that normal vector. Now we will talk later on how we can find the normal vector and the equation of the tangent plane as well. Okay. Let me ask you a simple algebra question. Okay. So if you have two vectors on the plane, v and u, can you find a vector which is perpendicular to both u and v? Excellent. Michael, yes, right. Very good. So u cross v is the vector perpendicular to the plane actually where the u and v lies. Okay, that's how we're going to find the normal vector. So in fact, the tangent plane contains, if you have a surface like this, the point, so that's the point x naught, y naught, z naught, right? So the tangent plane contains all the tangent line passing, the tangent line to the curve passing through the point. So there are infinitely many curves. You have a tangent line for those curves. They all form the tangent plane. Okay, so now we want to answer this question. How do we determine the tangent plane and its normal vector? Okay, so if we can find a normal vector, we can easily find the equation of the tangent plane. All right, so let's look at that question closely. here. That's the first slide here. So let's start with the function of one variable, right? So y equals fx. So there's something like that. That's x. That's y. So let's do it. You have a curve here, something like that. So that's y equals fx. So you have point x naught, and that's the point x naught fx naught on the curve. Write down the equation of the tangent line at this point x naught y naught. So how do you write the tangent point? You on the point normal form. So that is, let's say, take a point x y on the tangent line. So you get y minus that's y naught. So if you take x naught y naught, y minus y naught over x minus x naught is x prime x naught. The slope of the tangent there, f prime x naught. So that gives you equals y naught f prime x naught times x minus x naught. So that's the equation of the tangent line, right? That's simple, using high school calculus here. Now, then the normal vector to the curve at the point x naught y naught is f prime x naught minus 1. Why? So it's easy to find the equation of the tangent line. Now we want to find the normal vector to the curve at the point x naught y naught, which is actually f prime x naught. It's not immediately clear. Let me show you how that is derived. Then we will extend this idea to function of two variables, right? Okay, so here we are, the curve again. So that's your tangent line L there. Okay, so this is a normal line, which is perpendicular to the tangent line. So the slope of the tangent line is f prime x naught. Therefore, the slope of the normal line is minus 1 over f prime x naught. Remember that m1 times m2 is minus 1. So the m1 is the slope of the tangent line L, which is f prime x naught. So m2 is minus 1 over f prime x naught. So that's the slope of the normal line. So now we can write down the equation of the normal line, okay, which is the point normal form, y minus y naught equals, the slope is minus 1 over f prime x naught. We assume f prime x naught is non-zero times x minus x naught. Simple. Multiply this out, clear the fraction, you get x minus x naught equals f prime x naught times y naught minus. So because of the minus, you multiply minus here, you get y naught minus y. So that's the equation of the normal line. Simple. Now what I want to do, I want to put this into a parametric form so we can identify the normal vector. You would have done this many times in algebra, in 1131 as well. Okay, so let's put lambda equals y naught minus y, right? So if lambda equals y naught minus y, then the equation of the normal line in parametric form, parametric vector form is, so then x, this is lambda, so x equals x naught plus f prime x naught times lambda. So x equals x naught times lambda times f prime x naught. And y equals, so y naught minus y equals lambda, therefore y equals y naught minus lambda. Y equals y naught minus lambda. So if you look at the form here, this is the equation of the normal line. It passes through the point x naught y naught and parallel to this vector. So f prime x naught minus 1 is the normal vector. Okay? So that's where the f prime x naught minus 1 comes in. So now we can use this idea to function of several variables. Okay? All right, so let's see what happens in the function of two variables. Suppose that x naught, y naught, z naught is the point that lies on the surface. Okay, then the normal vector to the surface is x naught at x naught, y naught, z naught is that's df on dx at the point x naught, y naught, df on dy at the point x naught, y naught minus 1. Now, so it makes sense. So in the 2D, you have f prime x naught for a function of one variable minus 1. That's the normal vector, right? So in the 3D, when you have the surface, that the normal vector is here f subscript x, that is partial derivative of x with respect to x naught y naught. partial derivative with respect to y, x naught, y naught, and minus 1. So because you have f prime x, now the function of two variables, you have two components, partial derivative with respect to x and partial derivative with respect to y. So that is actually the normal vector to the surface at the point x naught, y naught, z naught. You calculate the partial derivative with respect to x first at the point x naught, y naught, with respect to y at the point x naught, y naught, minus 1, that gives you that. So that makes sense. So let me give you a proper justification how I arrived at this formula. So, okay, so here's the justification. I'll go and go back to that picture again to show you that actually it's a one-line proof. It's actually a one-line proof. In 2D, so you have two components, right? Vector has two components, and in 3D, you have three components. Okay, so have a look at this picture we looked at before. So this is the tangent line, L1, which has a slope of partial derivative with respect to x naught, y naught, right? So we have calculated the tangent vector before. The tangent vector along this line L1 is 1, 0, f subscript x. It's a df dx at the point x naught, y naught, right? Similarly, you can calculate the tangent vector along this tangent line L2, which is 0, 1, fy, f subscript y. That is df dy, x naught, y naught. That is the slope is fy, that df dy at the point x naught, y naught, in the y direction, right? So we know that normal vector is perpendicular to the tangent plane, so you take the cross product. The normal vector of the surface is the cross product v cross u. So v cross u, you have seen this many times before in algebra. There is ijk, that is v 0, 1, f, the partial derivative with respect to y at x naught, y naught, and 1, 0, f subscript x and at 0, 0, 1. So you expand this, you get the cross product, you get the formula we wanted. Okay? So we got the normal vector formula for the normal vector. So once you know the normal vector, we can very easily write down the equation of the tangent plane. So let me show you how the tangent plane can be derived from this. Okay, here's the calculation. It's pretty easy. So you have the surface here. Okay, let me draw the tangent line, tangent vector here. So at this point, say, so that's your tangent plane at this point. So the normal vector is n, which has this formula here. To find the equation of the tangent line, tangent plane, so take an arbitrary point x, y, z on the tangent plane, x, y, z here. Okay, so this is perpendicular, 90 degrees. So therefore, the product is 0. Okay, so therefore, so this vector is x minus x naught, y minus y naught, z minus z naught. That's this vector here. X minus x naught, y minus y naught, z minus z naught. X, y, z is an arbitrary point in the tangent plane. And dot product with the normal vector, that is partial derivative with respect to x naught, y naught, f df1 dy, x naught, y naught minus 1. Multiply this out, you get the equation of the tangent plane. Pretty straightforward. So that gives you x minus x naught times partial derivative with respect to x plus y minus y naught partial derivative with respect to y at x naught, y naught, and then plus x minus z naught times minus 1 equals 0. So that gives you the equation of the tangent plane. So as soon as you calculate the normal vector, you can very quickly we can write down the equation of the tangent plane. So I want to look at an example. Let me first summarize this in the next slide, and then we'll apply that formula. Okay, so tangent plane and surface normals. Suppose x naught, y naught, z naught is the point of the surface. Z equals fxy. Then the equation of the tangent plane at the passing through that point has the equation I have derived here. So that is reordered here. Z minus Z minus Z naught. So if you take that to the right-hand side, Z equals Z naught plus that df or dx at the point x naught, y naught, x minus x naught, and then df on dy times y minus y naught. And the normal vector is just calculate the partial derivative with respect to x and y at the point and minus 1. That gives you the three-dimensional vector for the normal vector at the point on the surface. Okay, let's do an example and see how we can calculate this. So here's the example. The function is defined by z equals fx minus x squared over 4 minus y squared. And you asked to calculate the equation of the tangent plane at the point 2 minus 1 minus 2. Okay. All right. So let's write down here z equals solution. Z equals minus x squared on 4 minus y squared. And here x naught, y naught, z naught, the given point is 2 minus 1 minus 2. Okay, that's the point on the surface. And you see that when x naught is 2, y naught is minus 1, you get the point minus 2 there. All right, let's calculate the partial derivative, dz on dx. Differentiate this with respect to x minus x squared on 4 minus y squared. So that gives you, you can differentiate term by term, ddx on minus x squared on 4 and dd y of minus y squared, that of course. So that gives you, this is when you differentiate that, minus 2x on 4 plus 0. Okay, and you differentiate with respect to x here. So that gives you minus x on 2, positive with respect to x. And that calculate the dz on dx at the point x equals x naught, which is 2, and y equals y naught, which is 1. So that gives you, substitute there, minus 2 over 2, so that's minus 1. That's the component, first component of the normal vector there. And now we do the similar calculation for with respect to y. Dz on dy, differentiate with respect to y, minus x squared and 4 minus y squared. So we don't get anything from the first component. When you differentiate with respect to y squared, minus 2y. Okay, so substitute x naught equals, x equals 2 and y equals minus 1. So that gives you minus 2 times minus 1. So that is 2. Okay. Now the normal vector is, so you need to see the paper. So the normal vector, you can straight away write down the, let me see that, you can see the slide there. So the normal vector is n equals, so minus 1 and 2, the last component is minus 1. So that's the normal vector. So now we need to find the equation of the tangent plane. So to find the equation of the tangent plane, so that's your surface. So that's your normal vector, that's your tangent plane, and that is n equals minus 1, 2, minus 1. And don't memorize the formula which I gave before. You can actually derive that easily from here. So that is perpendicular. That's the point. Given point here is 2. That point is 2 minus 1 minus 2. We take an arbitrary point x, y, z on the tangent plane, which take the dot product. Okay, so that gives you this vector is from the point x naught, y naught, z naught, x minus 2, y minus minus 1, and z minus minus 2. That's the vector on the tangent plane. Dot product with the normal vector minus 1, 2, minus 1. Yes, that's right. Thank you. And take the dot product. Yes. So I take the dot product and that equals 0. So multiply these out. So that gives you x minus 2, y plus 1, z plus 2, dot product with minus 1, 2, minus 1 equals 0. So that gives you minus 1 times x minus 2, minus 1 times, I move up a little bit there, minus 1 times x minus 2, plus 2 times y plus 1, and minus 1 times z plus 2 equals 0. So that gives you minus x plus 2 plus 2y plus 2 minus z minus 2 equals 0. You simplify that, get minus x plus 2y minus z plus 2 equals 0. So z equals minus x plus 2y plus 2. So you can leave it like that, or you can simply write this z equals, bring the other term there, minus x plus 2y plus 2. So simply using the dot product, we can easily write down the equation of the tangent plane. Don't memorize the formula given in the notes. So you just directly calculate that. So first step is to write down the normal vector using partial derivatives, and then take the dot product, you get the equation of the tangent plane. It's pretty easy in this way. Okay, so now we want to look at how we can use the tangent plane to approximate the surface. How do I get the minus 1? Because the formula gives you the last component is minus 1. You can use that formula. So the formula here is, let me write it down here. dz on dx evaluated at the point x equals x naught, y equals y naught, and z equals z naught. And then second component dz on dy, and the third one is minus 1. Third one is minus 1. So that you can use that formula there. So that's how it came from. Okay, so that gives the equation of the tangent plane. I'm going to now look at the, okay, I'll do that. I'll write it a little bit bigger. We find the particle and the last, yes, last component is always minus 1. Okay, but remember that any scalar multiple of that vector is also a normal vector, right? So you don't need to worry about, oh, last component is minus 1. You can multiply by any scalar, still it's a normal vector. Yeah, I have proved that before in the previous slide. Yes. Okay, so let's look at how we can use the tangent plane to approximate the tangent surface. Therefore, we can actually estimate the error involved in various calculations. It's a very useful in applications. So let's start with the function of one variable and see what the total differential approximation is. Okay, here's a function of one variable. The point x naught fx naught is on the curve, right? Y equals fx. Now we can write down the equation of the tangent line. We have done that. So which is the equation of the tangent line is y equals fx naught. We calculate, right? F prime x naught times x minus x naught. Okay. So around the point x naught, if you look at it, the tangent line is pretty close to the curve, right? If you look at any point closer to the x naught, so this height is pretty closer to the height of the curve, right? So therefore, the right hand side of the equation, that is the height of the tangent line. So at the point here, the height of the tangent line is given by the right hand side. So whenever the point x is sufficiently close to x naught, you can approximate the function, the curve, by the height of the tangent line. So that's what happens. So fx is approximately fx naught plus f prime x naught times x minus x naught. Okay, so if you bring that fx naught to the left-hand side, so fx minus fx naught, that is called the change in the function value, equals f prime x naught times x minus x naught. So that is called the differential approximation to the difference. Difference of the function value is approximated by the derivative at the point x naught times x minus x naught. That's the change in x. So for the change in x, you get the change in the function value can be approximated by a simple formula. Okay? Now, so geometrically, this approximates points on the curve near x naught by the points of the tangent line. So it makes sense whenever x is sufficiently close to x naught. Obviously, the approximation may not be good if you choose a point somewhere here. So you have a big gap there, right? So generalize this idea for function of two variables. So when you have a function of two variables instead of the curve, you have a surface. We are going to approximate it by the tangent plane at the point of the surface, right? All right, so let's do that and see what we get. That will be useful, you see, in a lot of applications. So if you have that, so let me draw a surface here. So at the point x naught, at the surface x naught, y naught, the function z naught is actually fx naught. Z naught is fx naught, y naught. So that's the point on the surface. So we approximate it by a tangent plane. So the equation of the tangent plane gives you this. Okay, this is a tangent plane, something like this, right? So we can height of the surface, that's the function value fx, y, can be approximated by the height of the tangent plane. So that's coming from the right-hand side of the equation of the tangent plane. Fx naught, y naught, that is the particle with respect to x at the point times the x minus x naught. That is the formula, the equation of the tangent plane. All right, so we are going to use that to find the change in the function value here. So the change in the function value, so fx, y, so bring that to the left-hand side, fx naught, y naught, that fx, y minus fx naught, y naught. That's the change in function value. Okay, so that can be approximated by this right-hand side, by these two terms here. So that is called the total differential approximation for the change in the function value. So given the change in the input x and x naught, x and y, you get the change in output here, delta L. That is given by this formula from the right-hand side of the tangent, equation of the tangent. Okay, so you can simply write this as a total differential approximation formula. This is called the total differential approximation formula for function of two variables. So I have written down in red here. So this comes from this term here. Let me put there another arrow here. So the first term is the partial derivative with respect to x, evaluated at the point x naught. And the change in the x is x minus x naught is delta x. So that comes from here. That is delta x. And this is partial derivative with respect to y. That's calculated at x equals x naught, y equals y naught. And the change in y is given by delta y. So this formula is known as the total differential approximation to delta x. So if we interpret this change in x and y as an error in the input, then we can find out the approximate error in the output. That is given by the change in the function value, big F here, delta x, fxy minus fx naught, y naught. That gives the change. So if you interpret the delta x and delta y as a small error in your calculation, that gives you the change in the output delta x. So we're going to use that to estimate the various errors in calculation. Okay, so let me interpret that in terms of the error here. So we are going to use the total differential approximation to estimate errors. Sometimes we want to estimate the maximum error or absolute error. Okay, so the error means the change in the function value big F, so absolute value delta F, using the total differential approximation formula, which I put down there in the previous slide here. Let me put it back here. So that gives you this df1 dx times delta x, df1 dy times delta y, and you take the absolute value of that. Now by the triangle inequality, you get it's less than equal to by triangle inequality. Triangle inequality. You get absolute value df1 dx times delta x, absolute value delta x, absolute value df1 dy times delta y. So now you can interpret this, given a function f of x and y, a function of two variables, one can interpret the change in the function of delta x as the error in the output, given the errors delta x and delta y in the inputs. Okay? The triangle inequality, absolute value, the a plus b is less than, a plus b is less than equal to absolute value a plus absolute value b. So we are using that property here. So if we interpret that x as the input and the output is the function value, so we can say that the absolute error is less than equal to this term by the right hand side of this expression here. So given the function f, one can interpret the error in the output, which is delta f, given errors in x and y, that their input, delta x and delta y, they are error. So let's apply this to a couple of examples and see how we can estimate the error. So even most of the practical application, you always have some measurement errors or some forecast errors and so on. Most of the problem you have to estimate the error involved in the various calculations, particularly in engineering and so on. Okay, so here's an example. It's on the slide there. Hope you can read it clearly. Yes. So a right circular cone is measured to have a height of 10 centimeters and a base radius of 30 centimeters. Okay. You're asked to use the total differential approximation to estimate the maximum error in the volume if the maximum absolute error in each measurement is 0.1 centimeter. So let me draw a little diagram. Right circular cone. Okay. Right circular cone. So let me call that the radius r and the height. So r is the base radius. Okay, and the h is the height. So we are calculating the error involved in the absolute error in the volume, right? So that's to estimate error in the volume. So that's the volume. So the volume B, so write down the formula, volume of the cylinder, right circular cone of the cone is V equals 1/3 pi r squared h. Okay. So there is an error in the maximum error is given. So the change in the radius. So it's given that that absolute error delta r is less than or equal to 0.1, and absolute value of delta h height is also less than or equal to 0.1 centimeters, as given. Okay. Now, so we're going to use the total differential approximation formula to estimate the error in volume. So let's write down the partial derivative with respect to r and h. dv on dr. So differentiate this, volume 1/3 pi r square h with respect to r. So that gives you 2/3 pi r h. H is a regarded constant. You can out. So you have 2r when you differentiate this. And similarly, so you can calculate this at the point dv on dr at the point when r equals base radius is 30 centimeters and the height is 10 centimeters. So substitute 30 and 10. So that gives you 2/3 pi. R is 30 times 10. So that gives you 200 pi. Okay. Now, we calculate the partial derivative with respect to, I'll do another page here. Can you see it? Yes. dv on dh. Now differentiate with respect to h. dh of 1/3 pi r squared h. So this time we are differentiate with respect to h. So that means r squared is regarded as constant. So that gives you 1/3 pi r squared. When you differentiate it, you get 1. Okay. So calculate the value at the point dv on dh at r equals 30 and h equals 10. Substitute in 1/3 pi 30 squared. So that gives you 300 pi, right? 30 times 300 pi there. Okay, so now using the total differential formula, using the, can you see it? Okay, using the total differential approximation formula, delta V, that's a change in the volume, that's the error. So approximately dV on dr times delta R and dV on dH times delta H. We want to find the absolute maximum error. So let's take the absolute value of that, both sides. So that gives you approximately, oh yes, thank you, dH. Absolute value of dV on dr times delta R plus dV on dH times delta H. Okay. Now by a triangular inequality, that's less than equal to absolute value of dV on dr R times absolute value of delta R, absolute value of dV on dH times absolute value of delta H. Okay. So we have calculated that these values here already. Plugged it in. So dV on dr, we calculated that, which is 200 pi times absolute value delta R. I'll do one more step here. dV on dH, what was dV on dH? Which is 300 pi times absolute value of delta H. Now it's given that the maximum absolute error is less than 0.1 centimeters. So that is less than 200 pi times 0.01 plus 300 pi times 0.01. So that gives you 500 pi times 0.1. So that means 50 pi cubic centimeter is the maximum error. So the maximum error in the calculation of the volume is 50 pi cubic centimeters. So that's how we apply the total differential formula to estimate the error in the output here is the volume. Okay, I want to do one more. That's this inequality. Yes. Yes, so that we want the upper bound. So that's you can get. All right, so let's do another example and see how we can estimate the percentage of error. Okay. Have a look at the second example. It's also given on the outline notes posted on Moodle. So this is because we take we want to find the maximum error. Okay, so absolute value gives you the bound. All right, so this question is on cylinder. So the dimension of cylinder are measured to the nearest millimeter using a measuring tape. So the radius is measured to be 5 centimeters, and the height is measured to be 12 centimeters. So what should we expect the maximum percentage error in calculating the volume V to be? So that's the question. Okay, so what that means, these dimensions are measured to be nearest millimeter, which means this: the absolute error in each measurement is at most 0.5 millimeter, which means 0.05 centimeter. So that's what is given. So if you read the first sentence here, the dimensions of the cylinder are measured to be the nearest millimeter using the measuring tape, which means the absolute is at most 0.5 millimeter, which is 0.05 centimeters. In other words, delta R lies between minus 0.05 and 0.05 centimeters, similar for the height as well. R and H, R is the radius, H is the height. So we'll try and apply the formula as we did before. So let's draw a picture here. We're talking about here cylinder, right? Okay. So the right circular cylinder. Yes. That's the nearest millimeter. So the error is up to 0.5. So the radius R, height H, right? For the cylinder. So the volume of the cylinder, let's calculate that. Volume of the cylinder is V equals pi R squared H. Calculation is similar to the previous example. Look, let's calculate the partial derivatives first. Here. Yes, the greatest the limit of that. Okay, so partial derivative with respect to R. So I can straight away write this 2 pi H, right? When you differentiate with respect to R, and when you differentiate with respect to H, you get pi R squared. Okay, now you can calculate that dV on dr. So what is the height measured here? So 5 centimeters, radius is 5, R equals 5, and H equals 12. Okay, substituted that in 2 pi, R is 5, and 12 here. So 120 there. When you evaluate that positive with respect to R. So now calculate it with respect to H, dV dr. Let's do that in the second page here. So dV on dH, evaluated at R equals 5 centimeters, H equals 12 centimeters, gives you pi R squared, so 5 squared, so it's 25 pi. Okay, now apply the total differential formula. Using the total differential approximation formula. I can use the absolute value formula. Delta V is less than or equal to dV on dr times delta R plus dV on dH times absolute value delta H. Okay, so we calculated that dV on dr, which is 120 pi times absolute value delta R, and dV on dH, which is 25 pi times absolute value delta H. So we know that absolute value delta R is less than 0.05. So that's less than or equal to 120 pi plus, time here 0.05 and 25 pi times 0.05. So that gives you 145 pi times 0.05 centimeters. Okay, so that gives you, okay, so what do we get if we multiply that? 275, right? Okay, we can keep that. We need to find the percentage of error. Let's calculate the volume at the volume of the cylinder at R equals 5 and H equals 12 is V equals pi R squared H, R is squared 12. So that is the volume cubic centimeters. So what we want to find here, maximum percentage of error. So the maximum error is given by in V is here. The maximum percentage of error, let me write it down. Maximum percentage of error is given by, so the maximum absolute value of the error, that's given, yes, divided by volume times 100. That gives you the percentage, right? So that gives you the maximum here, 145 pi times 0.05 divided by pi times pi squared times 12 times 100. So if you simplify that, you get that answer, which is I think approximately, I don't know where I calculated this, 2.42%, I think. 2.42. If you use the calculator, you have this here, 145, 725 there, right? Yes, 725 over 100, and then you multiply that 100, you get to 2.42. Okay, so that's how you calculate the maximum percentage of error. Okay, so now, so we're going to look at chain rule formula, how we can use chain rule formula to do some complicated calculation. So let me start with the chain rule formula with the high school calculus here. The function of one variable. Let's look at the function here, y equals et squared. I'm pretty sure you all can write down the derivative straight away. Dy on dt here. Dy on dt is obviously 2t e to the t squared, right? So how we got that? So we'll use the substitution u equals t squared. If u equals t squared, then y equals e to the u, right? Then you apply the chain rule formula. So how do you apply chain rule formula? First differentiate with respect to u, dy on du, and then differentiate u with respect to t, du on dt, right? So so dy on du is e to the u, right? Du on dt is 2t. So you go from y to t in this way. So that is dy on du times du on dt. dy on du is e to the u, and du on dt is 2t. So that gives you, substitute for u, e to the t squared times 2t. So that's how we calculate that the derivative with respect to t for e to the t squared, right? Using the chain rule. Simple. So what about for function of two variables? That's the question we want to look at now. This is for the function of one variable. That's how we apply the chain rule from after substitution from y to t. You have this multiplication dy on du times du on dt. So we're going to have the similar formula for function variables. Here's that formula. We can give you a justification using the total differential formula. So we are looking at function of two variables x and y, and x depends on t. So in the previous example, u depends on t, right? U equals t squared. So x depends on t, and y also depends on t. So let's look at the diagram here. So you can get two ways you can get to t here. F to x, and then x to t, and f to y, and y to t. Okay, so that gives it here this part df on dx. You can calculate here dx on dt. You add them up, you get the formula. So to compute df on dt, the sum of the paths left to right from f to t and multiply the derivative. So here in this part, df on dx times dx on dt, that's the first component. Here, for in this part, df on dy times dy dt, that's the second component. You add them up, you get the formula. So we have two paths here to get t, because you have two partial derivatives here, df on dx and df on dy, x and y. Okay, let's apply this formula to an example. How did I get the formula? Let me give us a little justification for this. Here's the justification from the total differential calculation we have done. So the total differential approximation formula is given here. df equal df on dx times dx plus df on dy times divide by delta t. Delta for delta t, you have this expression here, right? So df on dt is the rate of change in f with respect to t here. So in the limit, that gives you df on dt. dx on dt, this gives you delta x on delta t gives you dx on dt. And delta y and delta y in the limit gives you dy on dt. So that's how you get the formula, this sum formula here. Okay, so let me slow down a little bit there. So let me go through again here. Yes, I see your comment. So let's go through this. This is a justification. You don't need to prove this formula. I'm just giving you how we arrived at the formula here using total differential approximation. Okay, so df this is the total differential approximation formula, right? You divide by delta t both sides, so you get that expression here on the right hand side here. And by the definition, when the limit df on dt as delta t goes to 0 gives you the df on dt. Okay, so in the limit, this term goes to df on dt goes to delta f on delta t goes to df on dt, and delta x on delta t go to dx on dt. Delta y on delta t goes to dy on dt. Okay, so you replace this by dy on dt, you get the formula which I described. Okay, I think we understand that when we apply it to some examples. Have a look at this example here. Z equals fxy is given by the formula x squared y. I'll stop it in a minute. X to the power 4, x equals e to the t, and y equals sine t, right? Okay, so Z has two components, x and y, and then x to t, and them up. Dz on dx, dx on dt, dx on dt here, and dz on dy, and dy on dt. Okay, let's calculate that. Z equals, I'm running out of time here, Z equals x squared y plus 3xy to the power 4. Differentiate this with respect to x. You get 2xy plus 3y to the power 4. And differentiate that with respect to y. When you differentiate that dy of x squared y plus 3xy to the power 4. When you differentiate with respect to y, x squared plus 12xy cubed. Okay. So that's partial derivative. Now apply the formula. So, and also you can calculate the x equals e to the t. So that gives you dx on dt equals e to the t. Y equals sine t. So that gives you dy on dt equals cosine t. Okay. So now by the chain rule formula, so dz on dt equals dz on dx times dx on dt plus dz on dy times dy on dt. We'll do more example in the next class. I just finished this. I got just 1 minute over time here. So substitute it in, you get the answer here. What is dz on dx? So 2xy plus 3y to the power 4, and dx on dt is e to the t, and this one x squared plus 12xy cubed times cosine t. So that gives you the answer there by applying the chain rule. You can substitute for x and y, you get a function of t as well. Okay, you can substitute x equals e to the t, 2e to the t, y equals sine t, and 3 sine 4t times e to the t, x squared, e to the 2t plus 12, x equals e to the t, y sine cube 3 times cosine t. So that gives you the answer. We'll do more examples in the next lecture. So I will, as Daniel said, I will record that Monday lecture. That will be available the usual time, Monday at 3 o'clock, and notes as well. I'll post the solutions as well. So the Monday lecture will be recorded, will be available the usual time after the lecture. All right, I think I'm sorry I'm a little bit over time. I'll stop at this now. Thank you very much. Recording.